Hi, everyone. So far, we've been talking about the sensitivity analysis. So last time, we took some time to review some basic terminologies used in LP, linear program. And also, we talked about the dual price and how it can be used for the sensitivity analysis. So today, we will work on an example problem. And first, let me show you, let me share my screen. Okay. Okay, so first, okay, so today we will work on this example problem. So first, we will work on how to formulate the linear programming model for this problem, and then answer a series of questions related to the sensitivity analysis, okay? Okay, so how come I don't have any problem description here? Okay. Okay, so this is the one of the product mix example. So in this example problems, 5 different products. Those are the products A, B, C, D, and E. Those 5 different products can be manufactured, and each product requires time on each of 3 different machines, machine 1, 2, and 3. Okay, so those are the machine time requirements. And the unit is minute per pound. And also this table shows 128 hours each week are available on each machine, right? And there is a variable labor cost. Those are the $4 per hour for machines number 1 and 2, and $3 per hour for machine number 3, right? Okay, and the second table here provides a selling price and the material cost for each product, A through E, right? So it is assumed that any amount which are produced may be sold at the price of $5.4544 per pound, respectively, for each products here, A through E, and the material cost for products A and C. So $2 per pound, and for product B, D, and E, it is $1 per pound. The objective is to determine how many of each product has to be manufactured per week to maximize the total profit, okay? Okay, so let me split the screen so that I can use Microsoft Word, maybe. That'll be good. To write on. Okay, like that. Let me disable my camera, and I want to use the full screen like that. Okay, so probably this would be good, right? I hope all these numbers are good enough for you to see clearly. Otherwise, yeah, please refer to the PowerPoints, the class lecture notes provided in our class Canvas website. Okay. Okay, so let's work on the LP modeling. Okay. So the first thing, as usual, is defining the decision variable, right? Because it's very clear that we'd like to determine how many of each product has to be produced weekly. So we're going to define the decision variables. Like, let's say A stands for the quantity of product A to be produced. Of course, the unit would be the pound per week, okay? Pound per week. Likewise, we can define B as the quantity of product B to be produced, okay? Likewise, C, D, what's going on? Why does it not allow me to write anything? Okay, so it's going to be D and E, okay? So those are the quantity of product C, D, and E to be produced. So we need these 5 decision variables, okay? Then our objective is maximize the total profit, right? So maximize total profit 1 year. Okay. So we want to maximize the profit. Right? From manufacturing all of these products, A through E, right? Okay, but then the question is, how would you get the individual profit for each product? So if you produce product A, for example, what's going to be your profit? So if you produce product A, your profit going to be the selling price, right? Selling price minus material cost, right? From here. So material cost minus the variable cost, which are given here, right? The labor cost. So that's the variable labor cost. All right. And here, product A may be sold at $5 per pound. The material cost for product A is $2 per pound, right? And the variable labor cost, the $4 for product, for machine A, machine number 1, and machine number 2. And it's going to be $3 for machine number 3, right? And the thing is, each product requires machining time for each of these 3 machines, right? So those are provided here, right? And also important thing, is machine time requirements using different unit, which is minutes per pound. Okay. 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 So. Let me, write down this first. So here, if you produce product A, then the profit would be right here. That's going to be first the selling price. That's going to be $5 per pound, right? Minus the material cost. That's going to be $2 per pound, right? Minus, we need to consider the labor cost, variable labor cost. So that's going to be the labor cost for machine 1 plus labor cost for machine 2 plus labor cost for machine 3. Okay, you have to provide this. Then how'd you get the labor cost, variable labor cost for machine number 1? That's going to be $4 right here. What's going on? So $4. It's going to be $4 per hour, right? And how many minutes are required? Let's say 12 minutes are required, right? For machine number 1. So that's going to be $4 per hour or per 60 minutes, right? Times here, 12 minutes per pound, right? So that's going to be the variable labor cost for machine number 1. So similarly, you can get the labor cost for machine number 2. That's going to be $4 per 60 minutes times 8 minutes per pound. Okay. Similarly, labor cost for machine number 3 is going to be $4 per 60 minutes, right? And then 5 minutes per pound, right? And then how much is that? That's going to be 4 times 12, 48 divided by 60. And what about this? 32 divided by 60. This one. Oh, I think this should be 3, right? Because here, $3. So it's gonna be 3 instead of 4. So it's gonna be 15 over 60, right? So that's the labor cost. And then I'm gonna just copy down here. That's gonna be 5, right? Minus 2 minus this. Okay. So how much is that? It's going to be 3 minus 48 plus 32 plus 15. 95 over 60, right? So how much is that? 85 over 60, right? So 85 over 60, that's 1.417. So that's going to be $1.417 per pound. Okay. So that's the profit for producing product A. Okay. So, okay. What you need to do is also you need to get the profit for producing all the other products, B through E. Okay, same way. So let's do that one more time. So now, if you produce product B, then the profit would be again selling price minus material cost minus variable labor cost, right? So that's gonna be $4, right? Minus $1, right? Minus labor cost. As we did before, we need to break it down to each machine, right? So that's gonna be 4/60 times 7, right? Plus 4/60 times 9 minutes, right? 3/60 times 10 minutes, okay? Of course, this number 7, 9, 10 from here, right? 7, 7, 9, 10 for product B, right? Okay, so how much is that? 3 minus 28/60 plus 36/60 plus 30/60, okay? Then again, that's gonna be 28, 36, 30. So that's 94, right? 94/60. So how much is that? Oh. 1.5666. Oh no, oh, what am I doing? Okay. So that's gonna be 180/60, right? So 180/60. How much is that? That's gonna be actually 86/60. Okay. So instead of 94, I'm gonna use 86. Okay, it's 1.43. So that's 1.4333 per pound, right? That's for the producing product B. Okay. Let's do one more time for producing product C. Okay. So if you produce product C, then the profit would be 5 minus 2, right? Minus 4/60, right? Times 8, right? So we use this 8 plus 4 over 6, 60 times 4. 3 over 60 times 7. Is that right? So how much is that? It's going to be 5. Okay, it's going to be 3 minus 32, 16, 21 over 60, right? 3 minus, how much is that? Okay, 32, 16, 21. So it's 69, right? Over 60. So that's 180 minus 69, right? So 111 over 60. How much is that? $1.85. Okay. So that's 1.85 per pound. Is that right? Okay, so well, I cannot scroll down. Okay, I know what to do. Cut it out, and then I'm gonna have some page breaks a couple of times. Okay. Now I can scroll down here. Good. What's going on? Okay, so here, so I want you to complete the same calculation for producing product D and E. So from my previous calculation, okay, so those values are, so for D, the profit would be 2.183, and for E, that's gonna be 1.7 per pound. Okay. So if we put them in the objective function, then our objective function would be maximizing, what do you say? Okay, 1.417, right? So 1.417 times A plus 1.43. 1.43 times B, and then 1.85 times C, right, from here, and 2.183 times D, 1.7 times E. That's our objective function then, okay? So please make sure you know how to get all of these objective function coefficient values, okay? Okay, then what constraint do we need to consider? there is a restriction on machining time, right? So we have three constraints, one per each machine, machine 1, machine 2, and machine 3, right? So for machine number 1, it will be 12 times A, right? From here, right? 12 times A plus 7 times B plus 8 times C plus 10 times D plus 7 times E, right? 7 B, 8 C, 10 D, and 7 E, right? But there's only 128 hours per week available on machine number 1, right? So this is gotta be less than equal to 128. Is that correct? Not exactly. Why? Okay, so you gotta be careful here. The constraint coefficients on the left-hand side are minutes per week. However, the right-hand side is hours per week, right? So you need to make sure that you're using the same unit, okay? Stick to the single unit. So what you need is, you just need to multiply 60 minutes here, because there are 60 minutes in an hour, right? Or you can divide by 60 on the left-hand side, either is fine, okay? So how much is that? 128 times 60. 128 times 60. 7680. Okay, so this value 7680. That's the right-hand side value then. Okay, so that's the first constraint for machine number 1. So likewise, we're gonna have 2 other constraints for machine number 2 and machine number 3. So we're gonna use all of these values, right? And the right-hand side value would be 128 times 128 times 60 and 128 times 60 as well. So here, let me write it down. 8A plus 9B plus 4C plus 0D plus 11E should be less than or equal to 7680, same right-hand side value, right? Likewise, 5A plus 10B plus 7C plus 3D plus 2E less than or equals 7680. Okay. And what do you miss? Non-negativity restrictions, right? So all of the decision variables, A, B, C, D, and E must be greater than or equal to 0, right? And I believe I have this complete LP model in our next screen, right here, okay? Of course, if you input this, the Lindo or Lingo, then you will obtain the optimal solution like this. And the ranges information, we talked about this last time, right? Objective function, coefficient ranges, allowable ranges, also the allowable ranges for the right-hand side values, right? And last time also, I showed you how to obtain this final optimal table from Lindo, from classic Lindo, okay? And today we will also talk about how to use these reduced cost, dual price, and slack variable values, everything, okay? Okay, so later on, we are going to answer for these 5 different questions, okay? So before answering for this series of questions, let's talk about a couple of fundamental terminologies used in the sensitivity analysis in linear program. I believe we've talked about most of them already. Okay, so the first one is reduced cost. So if you run LindoLingo, it always provides us the reduced cost information for each non-basic variable, okay? So the reduced cost of a non-basic variable is the rate of deterioration of the objective function as the variable is forced to increase by a small amount. And it is the rate of deterioration of the objective function per unit increase in the value of the associated non-basic variable, okay? Okay. So, of course, in a maximization problem, like our example, the reduced cost gives the rate of decrease in the objective function value, but in the minimization problem, it will give you the rate of increase in the objective function value, okay? And so, of course, here, the reduced cost of a basic variable is going to be 0 all the time, okay? So here we have 3 basic variables, right? Those are C, E, and the slack 4 that has the positive value, right? So the reduced cost value for those basic variables is 0. Also, if you look at the final optimal table, the basis, that's the basic variable size, does include C, E, and slack 4, right? C, E, slack 4. That is the current value of 512 and 3072. That's the identical information, right? Okay, and the next one is about the dual price. So we also talked about this, right, last time. So according to the Lindo's report, the dual price is the amount by which the objective will be improved given a unit of increase in the right-hand side of the constraint. And last time I also mentioned that this definition applies only if the changes in the right-hand side of the corresponding constraint leaves the current optimal solution remains feasible. In other words, this dual price is valid only if the corresponding right-hand side values changes within the allowable ranges, okay? So if you want to use the dual price, always check the allowable ranges of the corresponding right-hand side values first. Excuse me. So dual price, okay, right here. So in our product mix example, the optimal solution report given by Lindo includes these dual prices, right? For each constraint. So let me ask you, so is this the degenerate solution? No. How do you know? Then how many basic variables do we have in this example problem? We're supposed to have 3, 1 for each constraint, right? And there are 3 positive basic variables. They are C, E, and slack 4, right? Also, the same information can be obtained from the final optimal table, right? C, E, and slack 4 are included in the basis. That's the basic variable set, right? Which means this is not the degenerate solution. The degenerate solution means that for a basic solution, if at least one basic variable has a 0 value, then the corresponding basic solution is going to be the degenerate solution. Okay. So when there is a degeneracy, what's going to happen? The next basis changes while implementing the simplex algorithm may not result in an improvement in the objective function value. Okay. Because the current optimal solution is not degenerate, this indicates that the profit will increase this much, about 23 cents per additional minutes of available time on machine number 1. And the profit will increase about 1 cent, okay? 1 cent per additional minute of available time on machine number 2, okay? And if you look at the dual price for the last constraint, it is 0, right? So if a constraint is not tight like this, the third constraint is not tight, right? Which means if the slack variable has the positive value like this in that constraint, right? The dual price must be 0. This is a consequence of the, what is that? The complementary slackness theorem. But this is understandable in view of the economic interpretation of the dual prices. That is, if a resource is not completely used at the optimum, so a constraint is not tight, right? Then the additional quantities of that resource will not result in an increased profit or decreased cost, right? So that is the corresponding dual price must be 0, okay? Okay, also the Lindo or Lingo provides the allowable ranges for the objective coefficient, right? So the objective coefficient ranges for each variable is the amount by which the objective coefficient can be increased or decreased without causing a change in the basis, okay? So last time we talked about this, right? This range indicates how far the associated objective coefficient may change before the current solution, before the current solution values must change to maintain the optimality, okay? So within these ranges, the current optimal solution remains the same. Okay. So in other words, within these ranges, both product C and E will be manufactured 512 pounds per week, right? And all the other products, A, B, and D, will not be manufactured at all, okay? Of course, the objective function value naturally changes when the objective function coefficient changes, right? Okay, and the right-hand side ranges, right? So right-hand side ranges for each row tell us within these ranges of values, the current optimal solution remains feasible. So some people says it is the ranges of feasibility, okay? In other words, the right-hand side ranges indicate how far the limiting value may change while keeping the same optimum basis, okay? And we've also learned that the dual price or the shadow price remains valid within these right-hand side ranges. Of course, assuming no other changes occur in the other right-hand side, okay? And okay, next is about the substitution rates. So last time we briefly talked about the substitution rates. And the here, the coefficients in the optimal table can be interpreted as the substitution rates, okay, in this following sense, okay. So suppose that the coefficient of a non-basic variable, okay, non-basic variable, which is xj, in row number I is alpha sub ij, okay. Then as this non-basic variable xj increases, the basic variable xi in row number I decreases, okay, decreases at the rate of alpha sub ij, okay, per unit of xj, okay. So again, as xj, one of the non-basic variable increases, the basic variable in that row decreases at the rate of alpha sub ij, okay? Let's keep in mind this, because we're gonna come back to this over and over while we are talking about the sensitivity analysis, okay? Of course, if alpha sub ij has the negative value, then this means that an increase in the basic variable, okay? Okay, so now let's answer for these questions one by one. Okay, so, okay, let me just make sure. Okay, I'm sharing my screen. Okay. Okay, so the first question, suppose it's necessary to produce 10 pounds of product A. So for use as a sample for customer, just for example, okay, then what will be the cost in doing this? Okay, so what will be the loss of profit in doing that? That is the question. So let's again probably use half screen like this. Okay. And okay, so what information we need to use to answer for this question? Reduce cost. So let me go back to that screen. Okay, so that's what we discussed, right? Just to go. So if we go to the optimal solution here, that's the reduced cost, okay? Provided by Lindo or Lingo, okay? So in the optimal solution, currently the A value, optimal solution, one of the basic variable, A has the 0 values, right? So A is one of the non-basic variable. The reduced cost of 1.379667, right? So this tells us that the profit will be reduced by the 10 pounds times this much, right? 10 pounds times this much, okay? So it's gonna be times 1.379667 per pound, right? So the question was here, right? So it asks if we are required to produce 10 pounds of product A, then the profit will be reduced by this much, okay? So that is the reduced cost. For variable A, okay? So if you produce 10 pounds of product A, then your profit will be reduced by $13, almost 80 cents, right? This much will be reduced, okay? Okay, then what if I suppose you want to produce 100 pounds of product D, okay? 100 pounds of product D. What if you want to produce 100 pounds of product D? What will be the loss of profit in doing this? In that case, again, you need to look for the reduced cost for variable D, which is this much, right? So in that case, the profit will be reduced by 100 times 0.075333. How much is that? Almost $7.53, okay, per pound. Okay. So the profit will be reduced by this much, okay? Okay, the next question, question B. So if you were to produce 10 units of product A, even though it is not optimal to do so, what will be the effect on the profit and the amount of C to be produced, the amount of E to be produced, and the amount of unused time on machine number 3. Okay, so what information we need to use to answer for these questions? Substitution rates. Do you remember? So we've learned substitution rate alpha sub ij indicates how much the basic variable x of I decreases, right, as the non-basic variable xj increases. Okay. So if you go back to the final table from Lindo output, if the non-basic variable A here increases by 10 units using this final table, we can answer the questions, right? So what I need is, okay, so that's the profit value, right? And this is the C, E, and slack 4, right? So let me write it down here. If the non-basic variable A increases by 10 units, then the profit will decrease by 10 times this much, right? 10 times 1.38. So how much is that? That's going to be $13.80. Okay. $13.80. Likewise, if product A is increased by 10 units, then production of C here, production of C will decrease by 10 times this much, okay? 1.267. So how much is that? 12.67, okay? Likewise, production of E will decrease by 10 times this much, 0.267, which is 2.67. Okay. But the slack time on machine number 3, which is slack 4, right, will increase because of there is a negative sign here. Okay. So the slack 4, that's the slack time on machine number 3 will increase by 10 times this much, okay? 4.4, okay? That's gonna be 44 minutes. Does that make sense? Okay, so now let's move on to the next question. Question number 3. So if 4 hours of overtimes are available on machine number 1 at a cost of $10 per hour, should it be used? So how do you answer for this question? What information you'd like to use? Door price. Is that right? So if you look at the door price, here, door price of a constraint is the rate at which the objective function value would improve, right? As the right-hand side of the constraint is increased by a small amount, okay? However, I told you the door price remains valid within the allowable right-hand side ranges, right? So first of all, you need to check if the changes amount of the right-hand side value is within the ranges or not, okay? So you need to look at the right-hand side ranges, allowable ranges, okay? So here, you are looking at the allowable increase limit, right? Here, 2671.304443. Okay. And what is the question again? Okay, so 4 hours. Okay, the important thing, the unit for this would be the minute, is the minute, okay? So 4 hours, the 4 hours is how many minutes? It's the 240 minutes. 4 hours, okay. It's 240 minutes, right? Okay. And there, $10 per hour. So there are 60 minutes per each hour. So it's going to be 10 over 60, 1 over 60. How much is that? 1 over 60 is 0.1667, right? Per minute. So those are the identical values, right? Okay, so the available increase limit is, this is the available increase limit. It's more than 4 hours, right? So with these 4 hours of overtime, the current door price for roll number 2 is still valid, okay? So what's the door price that you are going to use? This is the one, right? So the door price reported by Lindo for the row number 2 is 0.225833, right? Dollars per minute. Okay, so this tells us that if the company pays exactly this amount, right, for an additional minute, then there would be no effect on their net profit, right? However, if the overtime cost is less than this for an additional minute, the net change in the profit would be positive. Does that make sense? So the cost of overtime, which is 0.1667 dollars per minute, is smaller than the dual price of this, right? Which means the company must use the new plan because their net profit will be increased. Okay, that's how you can answer for this question. Okay, now let's move on to the question number 4. How'd you answer for this question? So it's been asking you what the most that the company would be willing to pay for another minute of overtime on machine number 2. So again, we need dual price, right? So we need to check if the corresponding changes of the right-hand side value is within the ranges. So we need to look at the right-hand side ranges. Yeah. So we need to look at this value, right? This time, you're looking at the value of 4388.571. That's the allowable increase for row number 3, right? So 1 minute of increment is still within the allowable increase limit of 4,388 minutes, right? So with 1 minute of overtime, the current dual price for row number 3. So still valid, okay? So we are talking about this dual price at the moment, right? Second one for row number 3. So the dual price for row number 3 is 0.010833, right? Minutes, sorry, per minute, right? Right. So this tells us if the company pays exactly this much for an additional minutes, then there would be no effect on their net profit values, right? So the answer is this. It's about 1 cent per minute. Okay, so now let's move on to question number 5. That's going to be the last question for today. Okay, so it's been asking you if 4 hours of overtime so again 4 hours would be the same as 240 minutes, right? If 240 minutes of overtimes are available, on machine number one. Machine number one, okay? The cost of $10 per hour. So previously is this much, right? So $10 per hour would be the same as 0.1667 per minute, right? How the production plan changes. Okay. So currently, let's look at the LP formulation. Okay, so we need to consider the second constraint. So it's this, right? So I'm going to write it down here. Second constraint, 12A plus 7B plus 8C plus 10D plus 7E, right? Is less than equals how much? 7,680, right? Okay, so by introducing the slack variable, we can get the equality constraint, right? So it's going to be 12A plus 7B plus 8C plus 10D plus 7E plus slack 2, okay, corresponds to the row number. Now we have equality sign, right? And then 7680. Is that right? And it does say if 4 hours or 240 minutes of overtimes are available, that means right-hand side value becomes 7,680 plus 240, right? And if we move this 240 to the left-hand side, then it's going to be 12A, 7B, AC, 10D, plus 7E, plus slack 2 minus 240, right? Equals 7680. Okay, so here, this tells us that in order to determine the effect on the production plan of increasing the machine number one usage by 240 minutes here, we must decrease the slack variable, which is the unused time on machine number one, from 0 to negative 200 minutes. Okay. See here, the current optimal solution, slack 2 has 0 value, right? So it has to be decreased to negative 200. So we know that one of the non-basic variable in this case, slack 2, right, decreases by 240 minutes, 240 units, right? So we'd like to know how this would change the production plan. So that's why I'm going to use the substitution rates, okay? So I go, okay, here. So what I need is to look for this column, right? Slack to column, right? Because I'm going to use all of these values right now. So this is how I'm gonna change it, right? Oh, what is that? Okay, so first row is about the profit value, right? That's the objective function value. And then we are looking at C, E, and slack 4, right? Slack 4. And the current value of those are this, right? That's going to be 1817.6, 512, 512, and then 3072, right? So that's the current value. And then I'm going to use this slack 2 column, right? Substitution rate. It's going to be negative minus 0.226, right? 0.183, negative 0.067, negative 1.15, right? Times what? The changes amount of negative 240. Okay, that's what you need to do. Okay. So I can get this value from Excel. Okay, so here, profit, C, E, and slack 4, right? The current amount is 1817.6, 512. Oh, what is that? 1817.6, 512, 512, 3072, right? Minus, right? And what's that? Okay, 0.226. Let me just write it down first. 0.183, negative 0.067, negative 1.15, right? And then I'm going to multiply by negative 240. So I'm going to drag it down here. So what I'm going to do is the profit will be change it to starting from this minus this value times this value, right? So that's the changed amount, right? Or what is that? Profit and the production of C and E and the unused amount for product 3, right? Okay. So with the use of the overtime, the product of the output of the product E definitely decreases, right? From here to here. And as you might expect, the output of the product C increases, right? Here. And the net profit would be this. Okay, I think that's it, right? Hold on a second. Let me just go back. Okay, just make sure. It's 4 hours. Okay, how would the the production plan change? Okay, so yeah, that's what you need to do. Okay, so these are all for today. And next time, I'm gonna give you another example problem. So just like we did for today, we're gonna start formulating the problem and then analyze the data, the result output, and then some answer for the series of questions related to the sensitivity analysis. And again, we are going to use all of these informations, okay? Reduce cost, dual price, the allowable ranges for objective function coefficient and right-hand side values, the substitution rates, okay? So please keep this information handy because we are going to coming back all of this over and over, okay? Okay, thank you everyone. So I will see you next time. Okay, bye.